If we're interested in fluid statics, that's the case where U, V, W are all equal to 0. And it gives us a trivial case where we can apply the Navier Stokes equations. So if I write the Navier Stokes equation for the x-axis, I have an equation here that allows me to figure out what's going on with the velocity under any conditions in any possible velocity field we could have. So certainly if this equation applies all the time, it will apply to the case where we have no velocity at all. So this term is the acceleration due to a global change with time, but the velocity is 0. These terms here are accelerations associated with fluid motion from one place to another. But again, the velocity is 0, so there's no motion. This term is our pressure gradient term. It's a force per unit mass due to pressure. It won't necessarily be 0. In fact, we expect to see a pressure variation inside our fluid, probably due to gravity. This gravity component in the x direction, that's the force per unit mass due to gravity. And then these are all the force per unit mass due to viscous forces. We've got the kinematic viscosity here, and it's multiplying all of these second derivatives of the velocity field. But if the fluid's not moving, those are all 0. So what we're left with is that the variations in pressure have to match up with the variations associated with gravity, so that we have a force balance, because if we didn't have a force balance between gravity and pressure, then our fluid would be accelerating. And it's not. Our acceleration is equal to 0. So if U is equal to V is equal to W is all equal to 0, then everything's going to cancel pretty well, and we'll be left with 0 equal to -1 over rho dp dx plus g of x. Or, rearranging, dp dx equal to rho times g of x. If we integrate that along some path, we'll get that the pressure is equal to rho g of x times the distance along the path in the x direction plus some constant. We can rearrange that by defining the constant to be p naught plus rho g of x, x minus x naught. Now if we take the case where the x-axis is oriented in the vertical direction, then we can wind up with g being just the total acceleration due to gravity, and we'll wind up with the difference, pressure locally minus the reference pressure, equal to rho g h minus h naught, where that's the change in height, as long as we've oriented that in the same direction as the x-axis. Finally, at the end of the day, we're going to say that change in pressure is rho g times delta h, and we're not going to worry quite so much about which sign it is. If we follow the sign convention very carefully, then we can get this analysis to tell us which way the pressure is changing. But more importantly, we're going to remember that the pressure always increases as we go downwards under the water. That's the direction of increasing pressure. So we can say that this equation here describes the difference in pressure between any two connected points in an incompressible fluid that is not in motion. So the 2 points need to be connected because we integrated along a path in the x direction through the fluid. They need to be an incompressible fluid because we used this version of the Navier Stokes equation where we made the assumption that the fluid was incompressible. And we need to be in a fluid that is not in motion because we made the assumption up here that U and V and W were equal to 0. Now, we'll actually be able to relax this one a little bit as long as we still find that all of these terms in our Navier Stokes equation, all of these terms that are associated with the inertia and the acceleration, are small compared to the pressure and gravity terms. So it doesn't necessarily require that things be absolutely still, just that they be very close to still. Finally, we need to remember that pressure always increases downwards and that we should always check our signs. We all know that the pressure is higher on the bottom of a swimming pool than it is out in the air above the swimming pool. So we know that pressure increases as we go downwards in a fluid like water. We will inevitably make sign errors if we try to keep track of differences in height and differences in pressure with signs attached to them. So when you're solving paper problems, always check your signs. Make sure that whenever you see a pressure difference, the pressure difference is going in the right direction.